Hi, in today's video, we'll be continuing our studies of combinatorics, and now we'll show the following properties of the Pascal triangle. So what is the Pascal triangle? The Pascal triangle was found and discovered to show the properties of the combination identities. So Pascal founded that you can draw the triangle, the binomial coefficients in this manner, and then you can see that if you add them up, it is 2 to the power n, which we have proven in previous videos, and also we have proven this identity in a previous video, where these two sum is equals to this. Now, Chu Shih Chieh, a Chinese mathematician, found that if you add this diagonal, it will equals to the next row choice. And so formulated in mathematics sense, it is this identity, and this identity is known as the Chu Shih Chieh identity, or also known as the hockey stick identity, where r choose r plus 1 choose r all the way to n choose r is the same as n plus 1 choose r plus 1. Another reformulation is r choose 0 to r plus k choose k is the same as r plus k plus 1 choose k. And we'll just show 1 and 2 is equivalent first, because r choose r is the same as r choose 0, r plus 1 choose r is the same as this, and in our case n here is just the sum of r plus k, and so n plus 1 is just the same as r plus k plus 1, and here will be the formulation to show that they are equal. And so 1 and 2 is the same, and you can use them any way you like when the question seems fit. So this proves that this way equals to this, which is the same as this equals to this. So it's the left hand side of the hockey stick or the right hand side of the hockey stick, they call it. So basically, let's now prove Chu Shih Chieh's identity. So we can see that on our right hand side is n plus 1 choose r plus 1. So obviously, like all combinatorics proofs that we have done in earlier videos, let us consider the set with n plus 1 elements. So the right hand side now, obviously you just need to choose r plus 1 elements, and we need to think of how we're going to choose these r plus 1 elements. So in our case 1, this 1 is chosen. So in our remaining n elements, we just need to choose r of them. Case 2, this is not chosen, and now 2 is chosen. So we have a remaining of n minus 1 here, and we just choose r, and we continue all the way to n plus 1 minus r, because at this stage 1 to n minus r is not chosen, and n plus 1 minus r is chosen, which only remains r elements left, and so you have only one way to choose, r choose r. And so we add them all up. It is basically our identity as shown, and hence this quickly proves Chu Shih Chieh's identity using a combinatorics proof. Now let's see some applications of Chu Shih Chieh's identity, and we'll take one simple one first, which is if you have 10 identical 10-cent coins and 15 identical 20-cent coins, how many different linear order arrangements are there if all 50-cent coins, all 15 of the 20-cent coins must be used? So basically, you just break your cases into no 10 cents, 1 10 cent, 2 10 cents, all the way to 10 10 cents. And then for the 15 coins, you have to put them in an arrangement, but since they're identical, it's just a choosing of the placing. And so at the start with no 10 cent, it's obviously 15 choose 15, because you have 15 coins and they're all identical, so you just need to put 15 into 15 slots. So it's just 15 choose 15. In our second coin now, we have 1 10 cent, so we have 16 slots. We just need to choose 15 of them to hold the 15 cents, 20-cent coins, I mean. So it's just 15 plus 1 choose 15, And we go on down to 15 plus 10, choose 15 when you use all 10-cent coins. And so when you add them all up using Chu Shih Chieh's identity, this is just n plus 1 choose r plus 1. And so this is the n. So it's 25 plus 1, which is 26. Choose 15 plus 1, which is 16. And so the total number of ways is 26. Choose 16. So we can see this is a direct application of Chu Shih Chieh's identity. And now we'll move on to a much more complicated example, but it's essentially the same thing. So we take an international math Olympiad, one of the hardest math Olympic competitions out there, and we consider this question, and we'll show that we can easily solve it using Chu Shih Chieh's identity applied twice. So basically, we consider the R element subset of the set of 1 to n, and each of these subsets have a smallest element. So we let the arithmetic mean of the smallest elements be defined as f n r. So we want to prove that f n r equals to n plus 1 over r plus 1. Well, let's first think about the problem. We have n elements, so we list them out first. Since we have to get r elements in a subset, our smallest subset must be when r minus n minus r plus 1 to n is chosen, in which case n minus r plus 1 is the smallest element. Because if n minus r plus 2 is the smallest element, then you can only choose r minus 2 left choices, and so there can only be a r minus 1 element subset. If you agree with that logic, you can continue listening. If not, you can replay the video. So, with the n minus r plus 1 as the largest of the smallest member, everything else below it is what we can choose for. We can set our cases to be, as everything above it cannot. And so, we will have 1 to n minus r plus 1 cases. So, our summation starts from 1 to n minus r plus 1. In this case, now let's think, if we choose a random element m over here, let's say, how many elements can we put inside to make up the r minus 1 set? Well, it can't be anything less than m, because these elements will be smaller than m, and we take m as the smallest element. So we have to, once we have an m here, we can only take elements from n minus m remaining choices. And so, these n minus m remaining choices, we need to choose r minus 1 of them. And that is the number of sets that m is the smallest element. And so, this is the number of times that m appears as the smallest element. And so we now want to take the sum of all these smallest, which means the sum from 1 to n minus r plus 1 times n of how many times they appear, which is n minus m choose r minus 1. And so we expand out, we can see that this is the expression. But we can rearrange them cleverly as we put n minus 1 choose r minus 1, n minus 2 choose r minus 1, n minus 3 choose r minus 1, all in one row. And then, since there are two copies of this, we can write another row with this starting, and we can add them accordingly. And we can continue down the line to the last row, and this row is the n minus r plus 1 row, and it will just be this remaining element. And so, our first row, we can apply the Chu Shih Chieh's identity to get n minus 1 plus 1 choose r minus 1 plus 1 elements, because this is the first term all the way to the last term. It's just reversed from the Chu Shih Chieh's identity. And we can see this just results in n choose r elements. For the second row, it now stops at n minus 2 choose r minus 1. And so it's n minus 1 choose r. For the next, it's n minus 2 choose r, and down all the way to r choose r. Now, since each of these rows need to be added up, we add all these rows together and it will be this expression, n choose r plus n minus 1 choose r all the way to r choose r. And so again, by the Chu Shih Chieh identity, you take this n plus 1 choose r plus 1, and hence the sum is just n plus 1 choose r plus 1. And so f and r is just n plus 1 choose r plus 1 over all the possible subsets, which is n choose r. And so n plus 1 factorial over r plus 1 factorial n minus r factorial must be divided by n factorial over r factorial n minus 1 n minus r factorial. And so these two will cancel out. You flip this to the top, r and r plus 1 will leave a remainder of r plus 1 at the bottom. n plus 1 factorial over n factorial will leave a numerator of n plus 1, and hence we get our identity that we want. And you have basically now been able to solve the IMO question if you have known the Chu Shih Chieh identity. And of course, a clever use of it. So you can see how the Chu Shih Chieh identity helps us solve very difficult algebraic problems and simplify them into combinatorics problems that we can use. And so I pose you the following algebraic identity, where double summation is just one summation times r plus m plus 1 choose r plus k plus 1. And you can see this is obviously going to be formed using the Chu Shih Chieh identity. And I'll let you practice this. In the updated notes that I'll be giving you guys, you have the solution already provided. And so you can take a look after trying it out for yourself. Thank you for listening, and I hope you have enjoyed my short video introduction into Chu Shih Chieh identity. If you like more, you can research about it online, as there's many articles and users about it. Feel free to like, share and subscribe, and leave any comments about any other videos that you want me doing about combinatorics. Thank you.